Okay, so may I start or?
Not yet, because I mean, I see that there are already something like, okay, how many are we now? 50? No, still not many people. Normally there are like 60 people.
Okay.
So we should wait a bit. Is that is right now is 4 sharp. Teresa, Pablo, Miguel Ángel, Joel, how are you doing, Ismael, Blanca, Alberto, Adrián? As I am saying, I am repeating all the time, but just do not hesitate contacting me on Teams and letting me know that you need 10 minutes just for, well, 10 minutes, half an hour, whatever you need, just to discuss on the assignment, and maybe I can help you, just very little, just conversation, and it can help you maybe, okay? Let me know. Hi, Miguel Ángel. Everyone is with groups, because I was sending also messages in the chat, because there were people that were asking me help for groups. So do not hesitate entering in Moodle and just, or even in the Teams here, just saying that you need, if you need people. I hope that you are now all grouped, because we are getting close to the assignment date deadline, but, and really along the week, just let me know and I will do my best, okay, to help you all. But the sooner the better, because otherwise, if everyone contacts me on Friday, it's going to be a little bit difficult for me to help. So how are you doing with Python? Because Lucia, you are going to go for Python, yes?
Yep. Yes.
How's everyone going with Python? Someone wants to talk? Everyone is mute. You can even write in the chat, if not. Lucia is going to put everything in Moodle, because Lucia, Miguel Ángel is asking if everything will be in Moodle. So Lucia has put all the slides in the Teams already, but in any case, everything will be in Moodle. If not yet, I am not sure if it is already up. If not yet, it will be right after the lesson. Yeah. Don't worry.
After the lesson, I will upload everything. I put it in the channel of Teams, in the files section, a folder that is called clustering, that you have all the material that we will be using today. So you can start downloading that, because it will be the data and the things that we will need for today's lesson.
Lucia speaking again, is that I don't know if it was my problem, but I was listening to you a little bit soft, but maybe it was my micro.
No, maybe, wait a second, because...
I don't know, maybe everyone is listening, maybe it's a problem of my micro, but of my headset, but everyone can listen properly to Lucia, the sound is okay? Say if not, please. It looks like everything is okay.
Yeah.
So don't worry, Lucia.
Okay,
it might be that I have normally the sound a little bit soft. Maybe it's in my side, because just not to listen to the PPP very loud. I have it very, so it's my problem.
Oh, okay.
Javier, we were asking if you could listen okay to Lucia, because I was thinking it was a little bit soft, but it was my problem, I guess.
I was just...
No, it's okay, Lucia. Everyone has said it's okay. Don't worry.
Okay, because...
Okay, so, yeah, I'm going to leave you now, because I think that there are 50 people already connected. So little by little, everyone will connect. So, well, just let me, everyone, introduce you to Lucia. Lucia is PhD student at the laboratory Medan in the Center of Biotechnology. She's just doing, she will tell you more about what she's doing, but in any case, she has been just researching for us for the last 2 years. And she's very much expert on Python, on clustering, and today's lesson is going to be dedicated, because you are saying all the time that you have just seen classification. I am sure that you are going to see also clustering. Lucia, maybe it is possible that they have not done, I don't know, they will let you know, maybe too much on theory of clustering, but in any case, the lesson is going to be very practical. We are going to see just how everything of clustering has to be done, especially in Python. Okay, but if you have doubts regarding the theory, well, Lucia will make a little bit of, theory, but if you need more theory because still you have not covered that part, please let her know, and she will go slowly into it. Is that we assume, because they have let us know, all the professors, they have already covered clustering for you. But if not, as I am repeating, let Lucia know, and she will do it smoothly, okay? So I'm not going to take you more time, Lucia. I leave you with all of you. Once again, before leaving, do not hesitate contacting me along this week at any moment on Teams. If you have any problem with the assignment, please do not wait till Friday, because then it will be too late, and maybe I will not have time to just be able to help you all. Okay, but at any point I'm just connected. This week I am not teaching that much. So on purpose, so I can have more time in any case if you need some tutoring for the assignment. Okay, so thank you. I'm going to leave you then the floor to Lucia. Thank you, Lucia.
See you.
Thank you all. Have a nice week.
Okay, so let's start with today's session. As you can see in the slide, we are going to be implementing clustering analysis. I thought you more or less knew some theory about what clustering is, but we will just see a little bit about the different methods, and you can stop me, interrupt me anytime you need if something is not being clear, okay? And also, I wanted to ask you before we start if you have Python installed to use, but I think yes, because Antonio already told me that you have seen some parts of data wrangling and visualization with him already. So I guess that you all have more or less current version of Python 3, more or less, and also we will be using libraries very well known. So if you are using Anaconda, for example, they will be already installed. It won't take long also if you need to install something, okay? So yes, let's start. What is clustering? Clustering is an approach that we use in data mining to, with the data that we have, form groups in which the instances inside a group are quite similar between them, but are dissimilar to the instances in other groups. Okay, so what we want to do is to minimize that intercluster distance and maximize that intercluster distance. Okay, so as you can see in the picture, the group have between its objects a quite small distance or a high similarity, and between groups we have a very high distance or low similarity. Okay, we normally use the term distance as the 1 minus similarity. Okay, it's just the opposite thing, let's say. So there are different approaches when performing a clustering analysis. As you may know, some of the most popular and the first analysis that were proposed was partitional methods, also hierarchical methods, density-based methods. There are also several techniques that may use both of them, several of them, in a multi-phase approach, because they use maybe first a partitional method and then a hierarchical or whatever, okay? But the methods that have evolved till today are usually multi-phase, because they implement one phase with one type of method and then another phase with another type. The most known one, I'm sure that you have all already seen, it's k-means. That k-means is a partitional method in which, given a number of clusters, what we call k-means, okay, so the k is for the number of clusters, we recalculate the centroids of the different groups that we form. The centroids are those points in the clusters that are, let's say, where the gravity is in, the points that represent the whole cluster, okay? Also, for hierarchical methods, the most common one is the hierarchical agglomerative clustering. And for density-based methods, one of the most used is dbScan, okay? The advantages of using, for example, a hierarchical agglomerative clusters before using, like, instead of using k-means, is that we don't have to provide the number of clusters, because usually what we do with hierarchical clustering is to build a tree that we call dendrogram, and we can see where is going to be the optimal number of clusters by representing that type of tree, okay? Also, dbScan is a density-based method, and therefore what we provide to the algorithm is two parameters that measure the threshold for the density between 2 points to be inside the same cluster, okay? So we don't provide the number of clusters, but the density threshold. That is represented by two parameters that are called epsilon and mean points. And also, one of the advantages of dbScan is that it allows us to have noise in the data, something that the other two were more strict about. For example, with k-means, we don't have any point classified or categorized as noise. They are all inside a cluster. So, in the practical approach that we are going to see today with Python, we are going to work with a data set that is related to patients suffering or not suffering a disease that it is called the chronic kidney disease, CKD, okay? What is this disease? This disease is also known as chronic renal disease. So it involves heterogeneous conditions that can damage the kidney. Some of the complications can include, for example, high blood pressure, anemia, weak bones, poor nutritional health, or even in the most severe cases, nerve damage, okay? So, having more insights or information about how the studied attributes are in the dataset that we are going to see can provide us some more insights to maybe detect not detect, because we are not doing classification, but to have a more clear vision of how the variables distribute between the patients. Maybe we can do groups of patients, and those groups can give us more information than just only if they are suffering the disease or they are not. Okay? So, you have the data set that we are going to work with already uploaded in the Teams, as I said. Okay, you can see it. It is give me one sec. Here, if you go to files in the teams, in clustering folder, is this one. Okay, we are going to work with that CSV. Okay, and all of the data. This is a classic CS, like not classic, but already very well studied data set that you can find in the internet and several web pages. It is there. Okay, it's not just a very secret data set. No, it's public. This dataset was designed for classification. So we have a target class in all the patients, that is if they are suffering the disease or they are not. And you may ask me, so well, why are we going to use this dataset to perform clustering? It's because of what I was telling you, because although that label, that target is providing us information, the rest of the attributes may provide us something else, okay? Some kind of information that we were not thinking before. So yes, this data set includes information about early stages of Indian patients. It was obtained in an Indian hospital in July of 2015, so it was 5 years ago. And there are a lot of works, as I have just said, that are researching in it, but for classification purpose. We have 40 patients. 2015 are ill, and 1,050 are not ill, are healthy patients. Well, are not ill of this condition, of this disease that we are studying. Maybe they have another thing, okay? And there are 24 attributes or classes that are going to provide us information. One of the attributes, the 25th, is the label, the target class that I was already telling you. 11 of these attributes are numeric and 14 are nominal. But we will have to deal a little bit when we upload the dataset to Python, to a pandas data frame, for example, because it is not clean. The dataset in the CSV has some things that have to be fixed, okay? But we will see, because very little things, not very difficult. So yes, just for you to have it in mind, what we want to do with this cluster analysis is to make groups of patients that can give us more insight of how the studied variables distribute between those groups, and check if we can make some other categorizations apart from it has the disease, it has not the disease. Again, in its origin, the dataset was thought to be used in the task of classification, and therefore we have this variable called classification itself that contains whether the patient has or not has the disease. But since we are going to analyze the dataset from a clustering approach, we have to remove that variable and start working with clustering algorithms without including it. For the visualization and to check how the clusters distribute within this classification, we will use it, but not for the implementation of the algorithms, because we don't want the algorithm to take into account that variable when forming groups, because we will be biasing it towards that classification, and we don't want that. We want, just with the variables and attributes that we have, see which groups can we form, okay? So we are going to divide all this process in 3 steps. First, we will be seeing how to load that data, prepare it, and see what it is in it. We plot the distributions of the variables and explore the data. We then will be performing the analysis itself, the implementation of the different clustering methods and algorithms, that we will just see 2 of them, because I don't want you to keep seeing different methods when it's not the purpose of today's class. But if you are curious, I can send you more, or we can comment a few more, because at the end they are all implemented quite similar. You just have to change the parameters, or for example, sometimes one method will be more suitable from one type of data and less suitable for other type of data. But at the end, when coding, the thing is quite similar, okay? And we will also evaluate, validate, and visualize the obtained results. So let's start with the data preparation and exploratory data analysis, where we are going to load, clean, understand, and process our data in order to have a very clean data set when we perform that implementation of the clustering methods. Okay, now I want you to open the way you are going to use Python. I highly recommend you that you use, for example, JupyterLab. I don't know if you know JupyterLab or not. I'm sure that you are all very familiar with Anaconda. So I'm going to check just one thing, 1 second. If you have Anaconda open, maybe you are using Jupyter Notebooks, that is here. You can also use JupyterLab, that I quite like it more than Jupyter Notebooks, because it allows me to a little bit of more features. I mean, I can have the folders and the files that I am going to use. I can see them. Also, I can open, for example, the CSV and check it out. I can also open a variable inspector, that I'm not going to use it today, but you can also, I mean, you have more features with JupyterLab than with Jupyter Notebooks. So I kind of like it better, but it's to your elections. I don't care what you use, but just to let you know. So we are going to use different libraries. I'm going to show you which ones again, and you can start importing them, okay? We're going to use pandas and NumPy for all the data structures that we need. Afterwards, we will use Matplotlib and Seaborn for all the visualization stuff. And then we need to scale our data, as you will see. And for that, we will be using scikit-learn standard scaler. Also from scikit-learn, we will need the PCA function. And then for the clustering methods, we will use scikit-learn cluster K-means and scikit-learn agglomerative clustering, but to represent those trees that I was talking about, we will need SciP cluster hierarchy, linkage, and dendrogram, okay? Because here, this one. With scikit-learn, we cannot automatically draw those kinds of trees, but we have already coded functions with SciPy, and for us it's more convenient because we don't have to program it all itself. And also for the evaluation, we will need Silhouette and this library that will help us with the elbow method. That I don't know if you are familiar with it, but we will see it. Probably you will have all of the libraries and modules installed. Just this one, I'm sure that is the most probable one that you won't have. So you can install it by pip or by conda, depending on what you are using. If you want to install it by conda, you can just do it by, one second, that is here. By saying conda install -c conda forge need. And once again, this will help us with the elbow method. If you cannot install it, don't worry, because it is just for one thing that you can also see visually. But if you can install it, better. So I presume that you have all already imported those libraries and modules. If you are using a notebook, you can also write matplotlib inline to visualize the plots just in the cell below that you have instanced the plot. And then we can start preparing our data and exploring the data. One thing that I haven't said, I will also upload to Moodle and to Teams this notebook, the one that you are seeing in my screen, but I will do it after the class, okay? So now you can write it and keep it clear and not just go pressing the run button. So to load the dataset, you can just do a pandas point with CSV that I have shown that you already did it with Antonio, so you may not have problem. And I wanted to ask you to get some information about the dataset before we continue. So I want you to know how many patients do we have. I think I already said that, but with coding, I mean, can you check it by using pandas? How many rows do you have there? Because as you see, each row contains one patient information. Then can you answer me how many variables are we studying and of which types are those? Are they numeric? Are they categorical? How many null fields do we have? So I give you 2 minutes to answer those questions. Okay, I saw that you asked me, but I didn't saw it, sorry. It is being recorded, the class will be uploaded in YouTube later, and I will share the notebook after the class. You can create your own notebook and then you can check it with mine, but we are going to do it at the same time, so there shouldn't be any problem. If you have it though, if I am going too quickly or something, just tell me, okay? Yes, the presentation will be uploaded too. Yeah, everything. So I guess you should have it now. I will go to the next slide. So one sec. You have that two ways, well, to know. You have a lot of options to know how many variables are there in the dataset and also how many rows. But one of the easiest way is to know the shape of the data frame that we have just loaded. That would be with point shape. Also, a very useful function from pandas would be .info that returns us all of the variables, how many non-null fields do we have according to that variable. As you can see, for example, the ID does not have any null, okay? They are all complete. And also the info method provides us the data type that it is in each variable, okay? For example, the ID is integer and then the age is float. The objects are the categorical ones. But we will see that maybe we have to fix some things, but okay, easy. Then also another thing that we can do is to set to see the head of the data frame that will show us the 5 first rows, and if we say T will be showing us the transpose matrix, so we don't have to see it horizontal but vertical. We can see the different values in each variable, okay? So the original dataset will have these variables in columns, not in rows, but this simplifies us the visualization, okay, of the different values. Okay, now that we have seen what we have inside, a little bit inside the data frame, I provide you a data dictionary with the different meaning of each of the variables and the features descriptions, what we have inside each variable and how it is measured, and if it is categorical or numerical. I have uploaded you in Teams variables renamed txt that it is containing some of the non-meaningful variables that have just 2 letters of name, which is the complete name of that variable, so you can rename it in the code. You can rename that variable with the complete or comprehensive name, so you can understand exactly, and you don't have to go back to the dictionary each time you need it. So as you can see, we have, for example, the age, some blood-related features as can be blood pressure, a specific gravity, albumin, sugar, red blood cells. We also have a red blood cell count that is not the same because here is nominal, and we just have if it is normal or not normal. Another things as can be more related to infections, for example, bacteria or past cells. A lot of things related to laboratory tests that have been made to patients, okay? So now I want you to rename those variables, as I told you, with the file that you have in Moodle, okay? One second, that I will, here. You can just copy that file and this one and just rename, that we will use the rename function. Okay, so I guess you have it now. Okay, there were some problems with both the red cells blood count, the package cell volume, and the white blood cell count that were set to object, so to categorical, when we need it to be numerical. Okay, so then you have to convert it to numerical variables. There are some fields that have an interrogation mark instead of an AND value, but as we will consider that interrogation mark as an AND, we use that parameter of the two-numeric, that is errors equal to squares, that will just don't take care of that interrogation mark and will just replace it with an AND value. Okay. So I guess you are here. One question, do you prefer me, I have all the code put it in the slides, but maybe you see it better in the Jupyter notebook. I don't know which thing you prefer. Which file you don't see, Bruno? The variables txt? txt?
Yes, I was talking about the txt. Yeah.
But did you find it?
No, you said it was a Moodle?
No, in Teams, sorry. Maybe I said.
Ah, in Teams, okay.
Sorry.
Okay, okay, thank you.
Okay, so is everyone at this point? We have the data set with some of the variables that we have converted to numeric because they were settled to objects, but it makes more sense for us to have it numerical. And also we have renamed some of the variables that were seen in Teams, sorry, not in Moodle. And yes, we have seen that we have one column that is the classification target. No, the slides are not in Moodle yet. The slides will be in Moodle, but in Teams, in the team channel, I am going to show you again. You have all the things that you need. Okay. Here. if I am going too quickly, just tell me, because it is easy, and I don't want you to get lost. Also, my English is quite so sorry for that. I'm so sorry. But okay, so I am going to go 1 second to the top of the notebook so you can see everything if you have just omitted something. That would be, we load our data, we import the different libraries that I think everyone got it. We load the dataset, we call it CKD init because I wanted to keep it the original data frame. So if I have to visualize something later, I will have the exact dataset as it is in the CSV. We check how many variables are there and how many rows do we have. Then we have also another function very interesting that is .info that give us a lot of insights of the data frame. This one .head.t was only to check which kind of data we have inside each variable. Then we renamed the different columns that have not a significant name. So when we are going to visualize the data and those kind of stuff, we have the entire name and not just 2 letters that don't say anything to us. So we use for that the rename function, and we are going to use another data frame that it is called CKD process. That is the one that will tell us that we are doing things to the data set, and it is not the same data set as we had in the CSV, okay? So I guess you are all here now. Then we have changed 3 variables to numeric because they were originally categorical, and as the things that they are providing us are numerical stuff, we need to convert them. Now what we're going to do is to remove the ID column because it's not providing information to us. It's just a number that says what patient it is in each line, but for the clustering algorithms do not say anything. So we drop that column with the function .drop. Till now we are only using pandas functions that I am sure that you saw the other day with Antonio, okay? So easy. Okay, now what we want to do is to know how many values do we have in each, different values we have in each of the features, okay? So for that we can do a loop around the columns and go check how many unique values that will provide by this function and unique. So I guess you have all seen which unique values you have, how many unique values, no which one, but how many you have in each variable. Now what we are going to see is different between the numerical and the categorical variables, okay? So I want you now to write it yourself, to check it, how many numerical unique values are in numerical variables and how many unique values are in categorical variables, okay? I give you 2 minutes and then I will show you, but we see. So just you have to check that the data type of that column of the data frame, it is of that data type object or of data type float, int, numerical, okay? And then check it. I created two lists, one for numerical features and another one for categorical features, and just see if that feature was of data type object, it would be categorical, and if not, it will be in numerical, okay? So then you have the two lists with the numerical features and the categorical ones. And now I want you to check what we have already done for all the features, how many unique values are inside the categorical features. It's just the same piece of code that you use for seeing how many unique values were in the features, but this time just for categorical. Okay, as you saw when seeing how many unique values were in categorical features, there were some kind of errors. For example, in diabetes, that we have some parsing things, issues that we can solve because this tabulador, I don't know in English, tabulator? No, I don't know. Here and here are distinguishing this node with this node, or this yes, for example, has a space, and we want every field that is just yes, no, or null, but not distinguishing those kind of things. Also in coronary artery disease or in classification, for example, there is here a tabulator after CKD, and we don't want that. So we just replace those values with the correct ones. Okay, as you can see in the 13 box or cell here. Okay, I guess you have it now, right? Now I will just plot the same thing to check that everything is correct now. As you can see, for example, we have just the 3 values that we were wanting, and here also in the classification variable we just have the two possibilities and not the 3 that we were seeing before. Okay, I will continue. If you didn't have time or something, just let me know and I will just put it in Teams, the code that we have, like the cell code, and everyone can step at the same time and not being behind, okay? So now I want you to check for missing values. Okay, if you remember, we can find the missing values with the pandas function that is null, okay? So we can just set the pandas data frame name dot is null dot sum to get all the number of the null values, and then we sort the values to check which columns have more null values, okay? So now you have this. I want you to plot the different variables and the different numbers of null values of each variable, okay? Okay, I guess you have it now. This one was the previous piece of code where we get the different columns and how many null values we have in each of them, and sorted by the number of null values. And now what I want you to do was to plot that, okay? To show the number of null values for each variable. I don't know if you have done it like that. There are multiple ways to do it. It's just some tools you have, okay? If you don't have this, it's okay. You will have it after the class. Can someone tell me what shall we do with null values? Do you know? Or I'm sure that you have seen it in the other subjects. Anyone? What shall we do with null values, with missing data? I think you are seeing it in the... For example, yes, you can remove the observation, that's right, or put the average also, yep. Or replace it with 0, with mean value, yep, or remove it, yeah. That's all right. There are then some more, not difficult, but more, how do you say, not as naive approaches that can insert missing values in a better way than we do when inserting the mean or just removing the observation. Here we cannot remove the observation, or we could, but we will be deleting a lot of rows. Okay, here you can see that, for example, we have 152 missing values for red blood cells. That is quite a lot, so we will be getting out a lot of data that we don't want to get out. Okay, so we are going to just do the naive approach that we were commenting, the inserting mean, not median as I put here, but mean. You can put mean, better than median. Okay. And the mode value for the categorical features, because we don't have a mean value for a categorical variable. Okay, so yeah, you can insert those by looping the list that we had before with numerical features and categorical features. Okay. Now we check with the same piece of code as we did before, and we don't have any null values. Okay, now. Now what I want you to do is to plot the numerical features distributions. Okay, so you can more or less see how well distributed are not well, but how are distributed the different numerical variables and attributes. So you can just plot it with one by one, or with the list of numerical features. You can do subplots figure, for example. That is what I would do. Make subplots and plot all in the same figure. And I want you to tell me which distributions you think that are skewed. Okay, I will use Seaborn isPlot for this case, and what I obtain is this. You can, as I said, loop around the numerical features, and plot them in subplots in the same figure, so you have them all together, or you can just go one by one as you prefer. But here you have my approach, okay? One thing that maybe if you have replaced the missing numerical values with the mean, this will be a little bit different because I replaced them with a median. So it will be a little bit different, but I think that not very much. Maybe you have here other values that, for example, for the specific gravity or for the blood pressure, you have other inside values or something, but it shouldn't change much. Okay, same thing for the categorical values, but looking around the previous list that we made, that was categorical features, okay? So this one. And instead of doing isplot, that is giving us the histogram of each variable, we will do count plot, and we will see how many patients with that value of that variable we have, okay? Anyone is lost? Because I can slow a little bit or send you some code if you are not here. We haven't started yet doing clustering. Okay, perfect. We are going to do it now. Now, more or less, we have clear which distributions we have for our dataset. Okay, you can see more or less how every variable is distributed, and the thing is that we are not taking into account the classification target. Okay, we will have to drop it before we start doing clustering, but I think you now all have this. You can see that most patients have values around the non-strained values, okay? So for example, for red blood cell, most of the patients tend to have normal values for that, also for past cells, or for everything, okay? Most patients do not have diabetes, so when we check the groups that are being formed after the clustering analysis, we need to see the different variables which values are taken in each cluster, okay? That is a very important thing, because not just to evaluate the clustering results with evaluation metrics, but to check whether the variables are dividing one cluster or another in their distribution, okay? So now just I wanted to ask you how many patients had the disease and how many didn't have them. This one I just put it for a percentage, but this is not really matter in us, because we know that we have more patients that are ill than that are not ill, okay? So now we're going to remove the label for the classification. I call this new dataset all num, I mean CKD processed all num, because it's the one that we are going to convert all the features in numerical variables, so we can implement clustering analysis with all the numerical variables. For example, k-means do not allow us to have numerical and categorical values. We could have k-modes, that k-modes will allow us having all of the categorical variables, but not mix them, okay? So that's why we are going to convert all the categorical values in numerical. And we will do that just by what we call one-hot encoding, for example, that is saying this value for this variable, 1 and 0, a binary encoding, and this other value for the same variable, binary encoding. We have it that way or not? We have it or not, okay? But first, what we'll have to do is what I already tell you, to drop the column classification. And we have to drop it also from the list of categorical features that we have. Okay, for transforming the categorical data to numerical data, we will use getDummies. This function is also a pandas function, and we will provide the data frame and also the columns that we want to convert to one hot encoding, let's say. Once we process the dataset, we have, for example, one column for each value of the variable diabetes, that were yes and no, and we have zeros and ones corresponding to if we had that value in that variable for that patient. Okay, and once you have transformed the categorical data to numeric, what we have to do is to standardize the data. And for that, we are going to use the standard scaler that we have imported from scikit-learn. That will give us will be the same variables, but with the mean center in 0 and the standard deviation set it to 1. So we have all normal distribution, but for all the variables, so we don't have any influence of those higher values variables over the others. Okay, for example, if we have two variables, one is for example the height of a person, and the other one is the weight. Height, we can measure it by meters or centimeters, and the weight in grams or kilograms. As the features, the variables are not measured in the same way, maybe one of the variables will be taking more steps, normal step, more weight in the implementation of the clustering algorithm, and we don't want that. We want all of the variables to take the same weight when implementing clustering. Okay, so that's why we use the standard scalar. There are also scalars, as for example the min max scalar, that you can also use that, but I personally prefer the standard scalar. So what I saw here was just to check all the statistical parameters of each column. I ran it to 2, so you can see that every mean is in 0 and every standard deviation is in 1. Because if we don't round it, it gets so many decimals, and we can't see anything. So, but you can see it without rounding it. It's fine to round it. Okay, next we are going to do the thing today that is clustering. Okay, we're going to implement both k-means and hierarchical clustering. And what I want you to show you most is how to choose the different, for example, in k-means, the number of clusters, and in hierarchical clustering, how you can plot the dendrogram. I'm sure that most of you may know this, but there are some important or very useful tools in Python that are very highly, how do you say in English? That you can do a lot of things with them, okay? Okay, k-means. I'm not going to go inside the details of k-means if you don't need that, because I think that you haven't already seen them, but if you need me to stop, I will stop. So just tell me if you need help or something, okay? I'm going to plot the slides now. I want you to instantiate k-means with the default arguments, so you don't have to give it any argument, just to see if you know how to do it. I'm going to show you. Here we are going to instantiate the k-means class of scikit-learn, and then we feed it to the dataset that we have just standardized. Okay. Here we would have the parameters if we need it. For example, we have different methods to start the iterations. So here we could specify it. Also, we can specify the number of iterations to till the centroids converts. Here we have to say also the number of clusters, but here the default parameters we don't have to say it. It's just set to 2, I think. And there are different things that the k-means class provide us. That would be the dispersion, what here we call inertia, that it is the sum of the squared errors of the different clusters. Also, we have the cluster centers and the number of iterations. So I guess that you have already run that. I am sorry because I said that the number of clusters by default was 2 and it is 8. K-means from scikit-learn settles the number of clusters to 8. As you can see in the cluster centers that we got, the numbers here represent the values for each of the variables that we have inserted into the algorithm. Okay, so this would be the variables of the value of the variables of the centroid points in each of the clusters. When I talk about centroids, cluster centers, all of these, I am assuming that you already know, but if you have any doubt, please ask me. Based on what you say, sorry. Based on what you said, the number of centroids is what we are going to see just now. I was just showing you how to implement k-means, but now I ask you, how do you think we can set the number of clusters? Have you already seen that? Elbow method, for example, yes, that's one. Another type of approach that we can use to settle that. Okay, elbow method, dendrogram for hierarchical clustering, yep, silhouette, yep, that's right. We can see the different silhouette metric for each of the clustering models, and then see which one is better. Yeah, I'm going to stop a little bit myself in this. So, choosing the appropriate number of clusters. We have the elbow method. In the elbow method, what we do is to get different models, so setting different numbers of clusters. We run the algorithm and return the model and get the sum of squared errors, what we call dispersion or inertia, that we already get it from the previous implementation. We get that metric for the different number of clusters that we have settled, and we represent it. And we choose to get the number of clusters where the curve, when we plot this, is more hill, I mean. So we get the one that is more vertical, the next number of clusters to where the curve is more vertical. That is what is called elbow method, because it makes like a curve like that, and we get just the one that is more vertical, that has a bigger, let's say, elbow or knee, if we see it the other way around, okay? The other one is silhouette coefficient. Silhouette is just a metric that measures how well a model distributes the clusters, how well are they cohesion with the other within the same objects in a cluster, and how well the objects of a cluster are separated of the other clusters. It's just a metric of how mathematically well are the clusters distributed, okay? The thing is that normally in clustering we don't have the ground truth as we do when we do classification. We don't have that, let's say, etiquetación, that those labels, okay? Sorry for my English once again. So we need to evaluate the clustering on how well the clusters that we have formed are distributed, and how well those clusters give us information, not just the evaluation metrics, but with the visualization, what information we get. with the visualization or the statistical information that the clusters give us. Okay. So for the elbow method, what I want you to do is to set a range of 1 to 11 number of clusters and run k-means and store the result for the inertia of each of them in a list, just as you see here. So we make a list that is called SSE for the sum of square errors, and then store in it all of the results for its k-mean implementation with a range of number of clusters from 1 to 11. So now you have this. We are going to plot those dispersion scores or sum of square errors that are the same thing across the number of clusters. Okay, so just plot the number of clusters that range from 1 to 11 in the x-axis, and in the y-axis the dispersion that we were mentioning. Okay, so here you have the same thing, and you obtain this plot. So you can see here it's already written in the Jupyter notebook that here the elbow is located at 3 clusters. So here we had the most let's say elbow. The difference between the dispersion of 2 clusters and 3 clusters will give us the way to cut. Okay, but if you are not sure when visualizing, because for me it's quite difficult sometimes to see where is the real elbow. Okay, so what I do is to call this function of the library that I told you at the beginning of the class that was called need. That if you don't have it, it's okay, it's all right, because for the example that we are running, it's fine. But sometimes it is interesting to have it and to use it when we don't know where exactly to cut. And here what you have to do is to say the range of the number of clusters, the dispersion that we have stored, and how is the curve and the direction. So I repeat here the x-axis, the y-axis, and then how is the curve, because we could also have curves like we call more often knees, that would be the other way around, or you know, other kind of elbow or knees curves. Okay, so then we are going to see silhouette. We have already seen the elbow method, and we are going to see silhouette that, as I already told you, is a coefficient that measures the cluster cohesion and separation. Okay, so here I want you to also calculate the different silhouette coefficients that we obtain in average for all the clusters in the different models when we settle different number of clusters. I mean, we have a silhouette score for each of the points in the dataset when we are performing clustering, and a lot of times we average all those scores of all of the different instances in the dataset, and we get that metric as a summarization of the evaluation of that model. Okay, so if we settle different numbers of clusters, for example, for 2 clusters we get 0.5 of silhouette, for 3 clusters we get 0.45, etc. But that number comes from the average of the different instance silhouette coefficients. Okay, so I don't know, you are not seeing. Okay, now what I wanted here to do is you to collect again the different coefficients for a range of number of clusters. Here, instead of 1 to 11, I will say 2 to 20. It doesn't matter. It's just because you see more plot, a bigger line in the plot with silhouette coefficients. Okay. Again, we are implementing cameos for this. Okay. And the one score that we are obtaining here, the silhouette score, is the average score for all of the instances. If we wanted to get just the silhouette score of one instance, as we will see later, we will get the function of scikit-learn that is called silhouette sample instead of silhouette score. Okay, I am seeing now that Hugo is having a question, that is, why you upper bound with 11 clusters and not the whole group of variables, 24? Why would you go to 24? Yes, you could, but I wanted to show you that with 3 we get a visual elbow. Okay, so we could go to 24, yes, but I just wanted to look a little bit closer to the 11 variables. Not variables, but the 11 clusters, sorry. But one thing, when I am, you have cleared that K here is the number of clusters, not of variables, right? Okay. Okay. Yes, I mean, we should take into account at least the number of dimensions that we have when we are performing clustering. Yeah, 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 yeah. You are completely right, but yeah, it was because if we increase the number of clusters, the plot visualization wasn't as easy as it is with 11. Okay, so same thing here. We plot the number of the value for silhouette. One sec here. We plot the number of silhouette for the different ranges of clusters. Okay, and we will obtain the curve, but it won't be an elbow method now because we will want just the highest silhouette here. Okay, so here. Okay, now what we want to do is to have an insight of how well the different clusters in each model are according to silhouette. Okay, so for that I wrote a function that is in the examples of scikit-learn. I didn't develop it, but it's just there. And I want you to copy it because it's in Teams, in the same folder as the other things, okay? Here. You can see it here. And this function will help us drawing the distribution of the silhouette samples score in each of the models that we are going to settle different number of clusters. So once you have it, just copy it or import it or whatever. And one thing that I wanted you to ask is if you all know more or less how can we plot something in 2 dimensions when it has, for example, like here, 20 whatever features, and we cannot represent it visually in 2 dimensions. Do you have any clue how could we do that? PCR, yeah, exactly, principal component analysis. There are multiple ways of reducing this dimensionality, but one of the most used ones is PCA in Spanish, that is principal component analysis. So we can summarize all the information that the different variables give to us in just 2 dimensions, and this will allow us representing the different obtained clusters into dimensions, although we have 20, 50, whatever, how many we have of variables, okay? So this is why here in the function silhouette analysis, you have a variable that is xPCA. That is the data set that we will perform in it PCA with 2 component analysis to be able to represent it in 2 dimensions. So we have just another function from scikit-learn that is PCA, and we settle the number of components to 2, and we store the model here. We feed it into the standardized dataset that we have, and we get an NumPy array that we convert to a pandas data frame that we store it in CKD PCA. That is the one that we will be passing to the previous functions in order to represent the data frame in 2 dimensions and visualize the cluster in the 2 dimensions, okay? So we will just provide the function with the NumPy array of the previous data frame. We will pass also the data frame of PCA and the range of different number of clusters. This I could have put range from 2 till 25, so we can represent all the features, and we don't have that assumption that we were discussing before. Okay. So I remind you that we have silhouette score for the average of the different silhouette samples of each instance in the different models when setting the number of clusters to different values. So here what we are going to do is to settle in the algorithm 2 clusters, 3 clusters, 4 clusters, till 8 clusters. And for each of the models, we will get an average score of silhouette. But we will also plot the distribution of the silhouette in each of the samples of the dataset, because not all the samples will be the same way of cohesion and separation from the other samples in a cluster. Okay, in the different clusters there are going to be different values for the different instances, but we usually take the average one. So I guess that you obtain something like this. Okay, here you can see that number 1 has very good values of silhouettes. By the way, I didn't say it, but silhouette varies from 0 to 1, no, from -1 to 1, but the optimal results, let's say, are upper to 0.7, from 0.3 to 0.7 are acceptable sometimes, and -0 we cannot accept that model as a good clustering model. Okay. So as you can see, the cluster number 1 in green here, it is having a good silhouette coefficient, and you can see it in the PCA distribution that it is almost very well, let's say, established. Okay, so the cluster, give me one sec. Sorry. Yes, I was telling that in a same model we can have a cluster very well cohesioned to the same cluster and very well separate to the other cluster, but we can also have in the same model another clusters that are not as well as the other one or regarding the cohesion and the separation. That is what silhouette is measuring. But we almost every time keep the average one, that as you can see here is 0.28 for this clustering model. But in some cases we could be interested in just some specific clustering groups, not in all of the groups, and we can take those that have a high silhouette. Okay. Well, I don't want to get more and more in this. You can see that setting different numbers of clusters vary the distribution that we get from silhouette and also the average silhouette score. I once again say that in the right plots, what we have is the PCA component analysis visualization, in which we summarize all of the dimensions in just 2 dimensions. When I talk about dimensions, is variables, features, okay? So this for camins and silhouette, but I mean silhouette and the elbow method can be used. The elbow method, we usually use it for setting the number of clusters, and we can use that elbow method for any of the algorithms that needs to settle the number of clusters. And we can also measure different metrics that we are most interested, not only the dispersion, the inertia, whatever you want to call it. And silhouette analysis can also help us determining the number of clusters, but we can do a lot more things with silhouette, because is it an intrinsic metric of evaluation? That I haven't said that. In clustering, we need to use intrinsic metrics, because we don't have external metrics to compare the results that we have obtained with the real results, because we don't have those real results usually. There are some metrics that we can use, as the F-score or the adjusted brand index. There are some when we already have the ground truth, but it is not the thing we want to do with clustering. With clustering, we want to get insights of the models that we have, of the information that we have with the models we obtain, but new information, not a classification system in which we can input new data and obtain predictions, okay? So, I'm going to keep in mind that we are, although it's not the highest silhouette obtained, we are going to get k-means with the number of clusters set to 3 for something that I want to do with you just in a few minutes, okay? Then hierarchical clustering can be implemented with scikit-learn, but scikit-learn, as I told you, doesn't provide us an automated function to represent those dendrograms. That those dendrograms are only trees that visualize the relationships between the instances in different branches, so we can see how closely are 2 instances, in this case patients, related, okay? We use the function linked to obtain the matrix that is going to give us the distance between the different points at first, and then clusters when we go agglomerating those instances. And we can plot it by the function dendrogram that you can see here. I'm going to go very quick. If you don't have time to code it yourself, this will be uploaded, so you can later just run it to see. If you have any doubt, you can ask me without a problem, okay? We would obtain this dendrogram introducing the algorithm, the standardized data that we already explained. Here it is colored by clusters. The algorithm is considering clusters where the larger distance in the tree is met. Sorry, here Okay, in English this is quite difficult for me. Okay, from a branch unification to another branch unification, here to this one, and this one to this one, the larger distance is where we would like to cut the tree and obtain two clusters. But sometimes maybe we can have more information cutting in other parts, and in that case we can set the color threshold to 0, and we are not biased by the colors, and we just get the clusters as we see it visually. I don't know if I am explaining myself. There are several things, nice things that we can do with this kind of dendrograms with the SciP function, that is to also to cut the tree not just in the very low instance, but in maybe some kind of aggrupations, and see how many branches do we have there, okay, as this one, for example. If we don't need the deep end tree, we can do something like that, okay? Also, we can do the same thing to represent them in the two-dimension plot that we obtain with PCA dimension reduction. But here, for example, we would obtain these 3 clusters if we settle the number of clusters to 3. That I wanted to settle to 3 because of something that I am going to see now, okay? But what I wanted you to keep in mind when we are talking about clustering is that, yes, we can have all those intrinsic methods or evaluation metrics that can give us some clue of how well the clusters are distributed, and that can provide us some kind of optimization for the different parameters that are in clustering. For example, here we are just seeing as parameters the number of clusters, but there are other algorithms that may have tons of parameters, and is not as easier as here. And these kind of metrics, of intrinsic metrics, can help us optimizing them, and will be good, a good starting point when we don't know which parameters to settle. And if we don't have a background in the scope that we are studying, for example, here in medicine, that will be cool to have those intrinsic metrics that can provide us mathematical background and not just knowledge about the field that we are working with. But at the end, when we have chosen a model and we have chosen that this model is our best model by just performing silhouette analysis, for example, we need to somehow determine which variables are different in one clusters and in others, to see why are we dividing those instances in different clusters. That is the main reason to do cluster, is to obtain that information that at once we wouldn't see. That some instances have all these properties in common because they all have high values for the variables, but low values for this other variable, and normal values for this other variable. Okay? Do you know the point I'm trying to make? So once we decide that we are going to keep this model or this other model, we have to do the most difficult task, let's say, in clustering, that is interpreting the results, and in some kind, if we can, we should give it a name or a proper definition to each cluster. A lot of times we can do that just by knowing the centers the centroids that we call of those clusters and which values of each variable take the centroid, and that would be we giving us information of the model difference in between the different clusters. Here, I wanted most of the models that are generated get the best results with 2 clusters, and that makes sense because it will be for us to think the CKD patients and the not CKD patients, those that are ill and those that are healthy. But that is not providing us much information. That is the information that we already have. So I wanted to just get not the best model, but one easy model that will provide us some other information, and that can be, for example, helpful to doctors. And maybe if we make a label with the obtained clusters, we can make another classification problem that it is also interesting for the physicians, you know. So get the k-means 3 clusters model just by instantiating the k-means class with the number of clusters setting to 3. Remember that we were working with the standardized dataset, and the obtained clusters will be in an array in the k-means dot labels. We have to convert this to a string because it doesn't make sense for us to keep it as a number, because it's just the name that we will give the clusters before we know which labels to give each cluster, which names to give to the clusters, but they are not numerical data, it's a categorization data, okay? So once you have the k-means with the clusters model, I want you to plot the classification and cluster distribution. So I want you to plot the count of the instance in the y-axis and the cluster in the number of the cluster or the cluster label in the x-axis, and I want you to differentiate them by color of the classification, I mean. So we can see how many instances of each classification go inside each cluster. So I guess you have something like this. We could do it with seaborn count plot, but we can do it with just a matplotlib if we like to, or whatever, it is fine. But I wanted to see that all of the healthy patients, let's say, are in cluster 0 with some of the ill patients. But for me, the more relevant information would be why are k-means splitting the patients in 2 clusters here. What relevant information can provide this separation for us? Okay, because here I figure that the patients that are going here but are ill are those that have the variables more close to normal. So they are maybe in an early phase of the disease, or maybe they have no much complications. But the relevant thing for me here would be to know which variables are differing in cluster 1 and cluster 2. Okay? One thing that we could do is to pair plot all all the relationships between variables and coloring them for the cluster. Okay, seeing the different colors for the cluster they are in. But well, here that we have 24 variables, it might be a little bit crazy. So I wanted to first know which variables are doing those separations. So for that, I am going to plot this 1 second. Which variables are dividing the patient in cluster 1, that in my case is represented in green because I use the palette set 1, but for you it doesn't have to be green, and cluster 2 that for me is red. Why are CKD the patients divided into what I was telling you? For this, what I would do first is to box plot the numerical attributes, box plot representing the clusters and the different values of the attributes, okay? And strip or swarm plot those variables that are categorical. Okay. Once I represent this, that I will show you now, I started thinking, okay, maybe there are some possible complications related to blood, or is there an infection? Because the variables that show more difference between cluster 1 and cluster 2 were, in the one hand, the ones related to blood, as can be red blood cells or hemoglobin or packet cell volume, and in the other hand, that there could be one of the clusters that had the thing in common that all the patients in it were infected because they have bacteria or past cell clamps. So I would go representing each of the variable if it is numerical in a box plot, so I can check the distributions and the different classification and the different clusters. So I can see which is the value for a healthy individual, how the individuals in the other clusters or in the same cluster but that are ill is related to the the healthy ones, okay? And I will go seeing that for each of the variables. If they are categorical values, well, this one is not categorical, but as it were, because it has only 6 or 7 values. But if they are categorical, or if they are numerical but with very low number of values, I would represent it by a street plot that I can see the different points that go in here, or by swarm plots that are these ones, okay? That I can see it more open and check the different number of points that go in there. And as I told you, you can see that cluster number 1 is having more health issues, more blood issues, sorry, because it has red blood cells settle most of them to abnormal, or for example, also they could have an infection because they have also past cell to abnormal and bacteria that is also here. You can see that they almost always have it present. Okay, so that is what I wanted to transmit you, that the important thing about clustering is the part of analyzing the clusters that have been formed, how the variables are distributed in each of the clusters. Okay, so I think it's time now. I will upload the notebook to both teams and models, so you can have it and you can run it. And yeah, if you have any doubt, you can ask me now or later or whenever you want. And Yes, I think that's all. I don't know if you want to comment anything. If you have any suggestion, I mean, I don't know how to do this easy for you now that we have online classes. Because I didn't want you to provide the notebook before the lesson, because I think if you have the notebook, you will go just executing all cells and not understanding anything. But what is your opinion? I want you to know, because if you think you would have been better with the notebook, maybe I think about it for the next classes to just upload the notebook before the class, and that's all. What do you think? Okay, yeah, I see your point that okay, yeah, I guess for the next time, maybe I upload it before the class. But yeah, okay, yeah, I think in sometimes it's better to have it. Anyways, I am going to upload it just right now, this notebook, so you can have it. And if you have any doubt or something about it, you can ask me. Okay? So I think that's all. It's time to. Yes, a question. Yes, of course. One question that you have is that would the results change with the transformation? Yes, if we don't scale the data, the results, or scale or standardize, whatever we have to do, wouldn't be the same. Some features that have higher values can be more important for the algorithm, and getting totally different results. Yeah. That's a good point. If we had more time, we could have checked that. Okay, so that's everything. Yep. See you all. I don't know when, but see you.